Hello and welcome to our podcast, Inside Malaria Biology, Breakthroughs, and Beyond. In this podcast, we delve into one of the world's oldest and deadliest diseases, malaria. Despite decades of control efforts, this mosquito borne illness continues to affect hundreds of millions of people annually, particularly in sub Saharan Africa and Southeast Asia. But the malaria story is evolving. Climate change, drug resistance, and new technologies are reshaping the landscape of both risk and response. From the complex biology of Plasmodium to cutting edge innovations like gene drives and AI enabled surveillance, the battle against malaria is no longer confined to bed nets and anti malarials alone. This podcast explores not only the biology and epidemiology of malaria, but also the tools and strategies that may finally tip the scales in favor of eradication. Let's begin. Segment 1: The Changing Face of Malaria, Epidemiology and Emerging Trends. The epidemiology of malaria is undergoing rapid shifts. Historically confined to tropical and subtropical regions, malaria transmission zones are now expanding or, in some places, re emerging due to climate change. Rising temperatures and altered rainfall patterns are creating new habitats for Anopheles mosquitoes, pushing the front lines of malaria transmission into previously unaffected highland and urban regions. Urbanization and internal displacement are also changing transmission dynamics as people migrate due to conflict, economic pressures, or climate impacts. They often settle in densely populated areas with inadequate vector control. This creates fertile ground for outbreaks, particularly in parts of Southeast Asia and Central Africa. Complicating matters is the growing threat of drug resistance, particularly to artemisinin-based therapies. Resistance has already been confirmed in Southeast Asia and is emerging in parts of East Africa, raising alarms about the future effectiveness of our frontline treatments. Moreover, surveillance systems in many regions remain fragmented or underfunded, making it difficult to detect and respond to shifts in transmission. Without real-time data, public health efforts risk being reactive rather than proactive. To address these emerging trends, we must rethink malaria not as a static problem, but as a dynamic and evolving change, one that demands adaptive, region specific, and technology driven responses.
Segment 2: Plasmodium and the Human Host, Understanding Parasite Life Cycle. The malarial parasite is master of survival. Among its five species that infect human, Plasmodium falciparum and Plasmodium vivax are the most clinically significant. Once transmitted through the bite of an infected Anopheles mosquito, the parasite begins a complex life cycle that allows it to evade both immune system and drug treatments. Inside the liver, the parasite undergoes a silent transformation, multiplying rapidly without triggering symptoms. For P. vivax and P. ovale, some parasites even enter a dormant stage called hypnozoids, capable of reactivating weeks or months later, making complete eradication even more challenging. Once in the bloodstream, Plasmodium evades red blood cells, replicating within and causing them to burst. This cycle leads to the classic symptoms of malaria: fever, chills, and anemia, but also enable immune evasion. The parasites can vary its surface protein, effectively outwitting the human host response and making vaccines development particularly difficult. Adding to the challenges is the rise of drug resistance. P. falciparum, in particular, has developed mutation in its CLNC13 gene linked to reduced sensitivity to artemisinin, resistance to partner drugs like piperacillin and lumefantrine, also emerging and raising fear of treatment failure. Understanding the parasite's biology, its life cycle, immune evasion tactics, and molecular targets is essential not just for developing treatment but also for crafting next generation vaccines and surveillance tools that can keep up with its rapid evolution.
Welcome to segment 3. Today's topic is vaccines, vector control, and gene drives, innovations in malaria elimination. The global fight against malaria is entering a new phase of innovation. After decades of relying primarily on insecticide treated nets and antimalarials, we now have vaccines that offer partial protection. The RTS ASO1 vaccine, marketed as Mosquirix, has been rolled out in selected African countries, while the newer R21 Matrix M vaccine shows even higher efficacy and is being scaled up rapidly. These vaccines are a crucial tool in reducing severe disease and mortality, especially among young children. However, vaccines alone aren't enough. Vector control remains foundational with long lasting insecticidal nets and indoor residual spraying continuing to deliver the highest returns on investment in high transmission areas. At the cutting edge of vector control are gene drive technologies. These involve genetically modifying mosquito populations to reduce their ability to carry or transmit malaria. Gene drives can either suppress mosquito populations or replace them with non infective strains, offering a potentially game changing approach, albeit one still under regulatory and ethical review. Combination strategies, vaccines, vector control, community education, and surveillance are proving to be more effective than any single intervention. The ultimate goal is not just control, but elimination, and that will require integrating these innovations across diverse ecological and epidemiological settings. While challenges remain, these breakthroughs signal a real opportunity to shift from containment to eradication if deployed equitably and sustainably. Thank you.
In this last segment, we'll talk about from diagnosis to digital surveillance, the tech revolution in malaria control. Diagnosis and surveillance are critical pillars in malaria control, and both are being transformed by technology. Traditional microscopy and rapid diagnostic tests, RDTs, remain essential, but newer tools are expanding the diagnostic frontier. AI powered platforms are now being used to automatically interpret blood smears, reducing human error and enabling faster results in remote settings. Mobile based apps and decision support systems are aiding frontline workers in diagnosing and treating malaria accurately. These tools can also collect patient level data in real time, feeding into national and regional surveillance systems. On a broader scale, digital dashboards and climate based predictive models are helping public health officials forecast where outbreaks are likely to occur. These systems integrate data from satellite imagery, rainfall patterns, temperature fluctuations, and human mobility, allowing for more targeted interventions. Genomic surveillance is also playing a growing role. By sequencing parasitic genomes, researchers can track resistance mutations and trace transmission pathways. This has been especially useful in identifying imported cases and in targeting residual transmission zones during elimination campaigns. As we move toward digital, real time, and predictive systems, it's clear that the future of malaria control will be shaped not only by biological insight, but also by data integration, cross sectoral collaboration, and equitable access to tech.